Hi, and welcome to the Plant Engineering Webcast, How to Minimize Machine Asset Downtime, Monitoring Systems in Real-Life Deployments, sponsored by Sensata Technologies. I'm your moderator, Gary Cohen. Happy to join you today on behalf of Plant Engineering. Here are some tips to help you get the most out of today's webcast. If you are experiencing issues with your slides or your audio, please refresh your browser or click the Refresh Media button directly onto the presenter's picture. You can control the volume of this webcast by adjusting the volume on your computer or by adjusting the volume on the webcast platform. If you're having any technical problems with the audio or with the slide presentation, just click on the question mark at the top right corner of your screen to access the list of system checks to try before contacting an online technician. If you do need a technician, just type a message in the Ask a Question box and someone will get to you as quickly as possible. If you have questions for our speaker, please type those in the Ask a Question box on the left-hand side of your screen. The live Q&A session will begin after the presentation concludes. Today's webcast is being recorded, and you'll receive an email within a week with a link to the on-demand event. To download a certificate of completion and a PDF copy of the presentation, use the Event Resources tab on the left side of your screen. Those documents will also be available with the on-demand version of this webcast. Now we're going to hear a word from the sponsor of today's webcast, Sensata Technologies. At the conclusion of the video, you may experience a few seconds of silence. That's just to compensate for varied internet speeds. Please stay tuned after the video for today's presentation.
Failed equipment is costing factories about $2.5 million per year. And shortcomings in today's real-time monitoring solutions cause 85% of assets to go unmonitored. The solution is Sensata IQ, an end-to-end asset monitoring platform. To monitor the health of rotary equipment, users can easily install Sensata's new multimodal sensor in less than 5 minutes and monitor that equipment on our IQ platform, which can predict machine failures, increasing productivity, and reducing operational costs. Minimize downtime with Sensata IQ, a complete platform for asset monitoring.
Excellent. All right, now off to the fun part. I am happy to introduce today's presenter, Abhishek Jadhav, a business development manager at Sensata. Abhishek is a mechanical engineer and Category 2 vibration technician. He has 16 years of experience designing and developing heavy-duty industrial products and holds a master's degree in mechanical engineering from the University of Alabama in Huntsville and an MBA from Wisconsin School of Business, Madison. Before joining Sensata, Abhishek worked at Fortive, where he designed and developed encoders and condition monitoring systems. Abhishek also worked at Caterpillar, where he designed and developed common rail fuel injectors and used in on and off highway trucks and power generators. Thanks so much for joining us today, Abhishek. The floor is yours.
Thank you, Gary. So before we begin our presentation today, I would like to give you a brief idea on the agenda for the presentation. So I will discuss, give a brief introduction about the company, and then I will also discuss various maintenance strategies, briefly introduce them. I will also talk about pros and cons of each one of them and why predictive maintenance is popular. And if you are a maintenance professional, it will not be a new information for you, but just hang on, it's not going to be very detailed. And I will then introduce about Sensata's offerings for the IIoT. And later on, we'll be talking about discussing real life applications or case studies on the sensors in action. So let's move forward. Just a little bit about Sensata. Sensata Technologies is a leading global industrial technology company that develops sensors and sensor-based solutions, including controllers and softwares and other mission-critical products to create valuable business insights for our customers and end users. Sensata has about 21,000 employees and operate in 15 different countries. And then our total revenue for last year was about 3.8 billion. We have about 1.1 billion units shipped under the name of Sensata and 21 other brand names that we own. We have about 47,000 products manufactured in two major business segments, the performance sensing and sensing solutions. We are the market leaders in automotive, HVAC markets, and industrial markets. We are also a major player in the worldwide electrical and power protection industries. Sensata has been around for a long time, more than 100 years, and we have served our customers and our partners as a reliable partner for them. So let's change gears a little bit. Let's talk about the maintenance strategies. There are four main types of maintenance strategies that are generally being practiced. The first one is called reactive maintenance, also known as fix it when it fails or run to failure type of maintenance. The overall maintenance cost for this kind of a strategy is very high. And the cost of production downtime is high because you run the assets to failure. For that reason, you must always keep a spares. That increases your inventory cost and also labor cost to repair the equipment after a catastrophic failure. The advantage of using this kind of a strategy is to reduce the cost of performing unnecessary condition-based monitoring. The disadvantage is that the asset will always fail. So when do you use this kind of a strategy? You use it when you have non-critical machines that are inexpensive to repair. The second type of maintenance strategy is preventative maintenance, also known as fix it before it is due to fail, or interval-based monitoring. And to be really honest with you, it can do more harm than good because high maintenance skills and spares management is required to do this correctly. The advantage of using this strategy is that it is ideal for assets with age-related problems, and when there's no cost-effective condition-based ways that can be implemented. But the problem is that it is often implemented on assets without age-related failures, and it is very costly. The unnecessary work is performed, which increases downtime, and it also introduces new problem. The third type of maintenance strategy is called proactive maintenance, also known as maintain it so it keeps running. The idea here is to do everything to reduce the likelihood of failure, including operating the equipment properly and conducting routine proactive maintenance tasks such as cleaning and proper lubrication. The advantage of doing this is eliminating most of the root causes that may cause equipment failure and to extend the life of the equipment. But the problem is it takes a support of management to be given at this time to perform the tasks needed instead of just performing the reactive tasks. And the last type of maintenance strategy we will look at is predictive maintenance, also known as condition-based monitoring of assets. It can be also described by a phrase, if it ain't broke, don't fix it. It involves testing the condition of the equipment to determine if the failure will occur in any foreseeable future so that the components in question can be repaired or replaced at the most convenient time. But let me clarify this. Monitoring the machine does not stop the components from failing, but you can extend the life of the rest of the assets by replacing that component that is failing at your next available time. So when do you use the predictive maintenance strategy? When it is possible to determine the asset's condition using some technology. It is more cost-effective to monitor the asset and plan repairs that allows to fail or overhaul it to the next scheduled basis. The advantage of predictive maintenance is to reduce the downtime, repair costs, avoid secondary damages, and also avoid the cost of keeping spares to increase the inventory costs. The disadvantage is that it takes an investment in instrumentation and training. It may also require additional staff if your current staff cannot be redeployed, requiring the change in mindset. So what are the good candidates for predictive maintenance? It's your 24/7 critical assets where the cost of downtime is high, your bad actors where there's a history of failure, and there are the other assets which are hard to reach where taking data of those assets could be a safety concern for your personnel. So what are the benefits of the predictive maintenance? If you look at this, this slide here, I'm just showing here an example of a typical electric motor. And there's vibration coming. We have a vibration sensor installed, and we're collecting data. The x-axis you see here is time in days and time to failure. So when you are at the beginning, you have like about 30 days. That's just an example, 30 days to failure. And once a problem has incurred, then you will start seeing increase in vibration. After time, you will start seeing evidence of wear, and then you will start seeing performance decline, then audible noise, and then it's going to be hard to touch. And then the motor fails. So if you look at the reactive maintenance at the bottom, there is nothing, no maintenance being done. And after the failure has occurred, reactive maintenance, you basically fix the machine. In preventative maintenance, you do routine maintenance to get rid of the defective or replace the critical part. You keep doing that, but then if you're not solving the right problem, you'll still have to fix the machine after the failure has occurred. In the condition-based monitoring, you will be able to see the vibration. If you are lucky enough to measure the vibration on time, you'll be able to see that problem, and then you can take the corrective actions. There won't be any failure. But with the predictive maintenance, any anomaly that happen in the vibration, you'll be able to detect it way early on, up to 3 months in advance, and then you'll have all the information about the remaining useful life because of this problem, where you can schedule a corrective action or at your most convenience time. So those are the advantages and benefits of using predictive maintenance. I'm going to give you a little bit information on the Sensata's IIoT offerings in a snapshot. It starts with IoT device, IoT smart sensors. We are sensor manufacturers at heart. You think about any sensor and chances that we will have it. For example, pressure, temperature, position, or vibration sensor. We have made our sensors smart, made them capable of connecting to the internet. Our smart sensors systems for industrial IoT applications easily turn any asset into a data source for valuable insights. We link our assets and collect insights to minimize the cost of monitoring plants, infrastructure, and building. Our machine insights platform, Sensata IQ, is an end-to-end asset monitoring platform that delivers valuable and actionable insights from Sensata's smart portfolio of smart sensors, connected sensors, to help plant operators avoid any sort of unplanned downtime, minimize the labor expense, and optimize their maintenance strategies. We have web and mobile dashboards that delivers all that information to you. So Sensata IQ is our AI-backed software platform, is at the core of machine health monitoring systems. We collect data from our new or any existing sensor sources and integrate that with the Sensata IQ platform and other ecosystems. Our sensors are easy to install. They're attached to existing assets to collect data. If you already have existing data sources, we can ingest that data from your sensors. We have advanced algorithms to deliver machine health monitoring and unlock predictive maintenance opportunities. We have dashboards review the data, but we can also import the data to a third-party services or cloud solutions. Our dashboard can operate as a standalone machine health dashboard, or it can be integrated into other world-class business platforms. Our goal here is to help customers reduce downtime while also cutting reliance on walkarounds or static preventative maintenance practices. If you currently offer walkaround services, we want you to spend more time analyzing the data and writing reports rather than spending time traveling to the customer sites. Our cloud solution has a built-in asset library of physics models, self-learning AI and machine learning models, device maintenance workflows, and then also we have user configurable dashboard. So let's look at where we can implement Sensata solution. Sensata IQ can be applied to industrial motors, blowers, pumps, fans, and compressors. Our AI physics models for these types of assets we have it for most of the failure modes, such as misalignment, looseness, unbalance, and bearing problems, which is about 90% of the problems we see in the field. Most of the problems are also lubrication related, and our sensors can detect all types of lubrication related problems. We can even see flow turbulence or any sort of cavitation related problems in pumps and fans. We are using the data to tell you about these problems months in advance to give you enough time to plan for that scheduled downtime. And according to a study done, people who practice predictive maintenance, 83% of the users have reported a positive ROI. So now let's look at some of the case studies. So first case study here, this case study is at a major automotive manufacturer. Their electric track motors that drive automotive assembly lines failed and stopped the production line. Whenever a motor fails, it takes about 40 to 120 minutes to repair or replace one of those motors. The cost of downtime was very high for these assembly lines. And at a production rate of about one car every 84 seconds, a single failure led to a loss of production of over $2.5 million. The final assembly line failed and stopped the production line at an average 2 times per annum. Each assembly line has about 500 motors and other assets such as gearbox that could potentially fail. There is no cost-effective way of monitoring these assembly lines, and converting these assets using route-based monitoring system was not highly effective because of the static measurements of the parameters to monitor these assets did not tell you the whole story in the past. And to give you an idea, the manual data collection with a handheld analyzer had been quoted at about 40 to 50K per annum for 1,200 sensors, which were taking data quarterly. So only 4 data points per assets per year compared to a data source of one per hour for each measurement points that can be covered through an online condition monitoring system. The car manufacturer turned to Sensata's solution. In the first phase, we fitted about 500 plus motors with our wireless temperature monitoring sensors. Our monitoring system can predict which motors are likely to fail, so preventative measurement maintenance can be done during that planned shutdown period. In the first 2 years since the installation, 6 instances of potential failures had been identified, and saving an estimated of $15 million in the lost production. We uploaded data from the existing wired sensors fitted to a conveyor track, gearbox to the Sensata IQ dashboard, custom designed for this car manufacturer in the second phase. And the acceleration waveform and the velocity RMS calculations were also displayed. And we set alarm limits and also alarm limits for the RMS vibration levels as well. So the car manufacturer now is looking at 4 levels of monitoring depending on how critical the assets are and what is the immediate budget available for this predictive maintenance. So they started with 6VW, which is our smart vibration sensor, to get anomalies detection and email alerts. We also installed wipe ports for route monitoring of assets where the dashboards using the existing vibration sensors that were already installed. We also had our wireless temperature transmitter with a 4 to 20 milliamp wired vibration for applications where they needed more trending of vibration RMS more than 4 to 6 times per day. Now the car manufacturer's assembly lines is fully covered using Sensata's solution to avoid any unscheduled downtime. So the second case study we'll see here, this is about a rotating oven OEM. The OEM oven system design did not meet strict temperature requirements for one of their sizable potential client. The OEM utilized slip rings with embedded thermocouples. The slip rings were inaccurate, had a wear cycle, and must be regularly replaced for normal operation. When the slip rings had crossed its useful life cycle, the system comes down, right? So the slip rings had typically been linked with thermocouples inside the rotating ovens, so they can give the information to the temperature controller. Replacing these slip rings with a short-range wireless link could improve the reliability of the temperature measured and the control of the oven, which also provides advantage over improving the reliability of taking accurate temperature readings, and then also allowing multiple in-process product temperatures to be monitored. There was a need to measure the temperature simultaneously and precisely. They asked us to measure the temperature at various stages. The temperature measurement needed to be precise. So we added our wireless temperature sensor with ISO slice inputs to transmit the data through thermocouples signals through the wipe port, and which was directly going into our from our gateway to our Sensata IQ platform. With our sensors, the OEM could replicate the system for all rotating ovens and other applications for slip rings, such as the sludge tanks. This eliminated the machine downtime for replacing slip rings and saved them labor time as well, improving reliability to take accurate measurements, temperature, and also improved temperature control of the oven. So now the OEM also won the business with their clients with which had the strict temperature measurement requirements as well. So this third case study, it's about an automotive OEM which offers water pressure sensing. So they provided a system that monitors 8 zones of water pressure during an automotive leak testing phase of the production. So the end users maintenance team manually logs the water pressure sporadically, creating safety hazards for the person who was taking the data at that time. They collected data once a month or once in 2 months, but the data collected is so sporadical and does not give you a full picture of the operations. They still have downtime and cannot avoid it. So they turned to Sensata's temperature measurement solution. We implemented wireless temperature monitoring solution that monitors and logs the water pressure in 8 zones of leak testing. These values were logged manually before for auditing purposes. So the automatic recording of and logging of this data saved person hours and also increased the data accuracy. It was easy and quick to deploy a wireless system, and the system delivered email alerts and provided real-time status for this asset. To give you more specific, we implemented our wireless pressure sensor, which enabled them 24/7 asset monitoring. The data is aggregated into an IoT gateway and then sent to the cloud where it can be formatted and used for any sort of alarming. The benefits of system where it eliminated the unforeseen downtime through continuous monitoring. It removed any burden on the manual walk-around process, eliminated the manual recording and logging of the data, and also provided alerts, for example, at the display, and then also email alerts as well if the pressure drops out of an acceptable limit. Avoiding downtime because of continuous monitoring and sharing of this data minimized the cost and also made the OEM look good. So the fourth wireless case study I'll be talking about is at a CNC machine manufacturer. In a CNC machine, a fixture is the work holding device. A hydraulic or pneumatic charging circuits clamps the workpiece in place, and any drop in pressure in the clamping system can lead to the workpiece moving, resulting in parts being incorrectly machined or becoming loose or detached. The fixture monitoring system monitors the pressure in clamping system, and one of the hydraulic charging circuits is once the hydraulic charging circuit is withdrawn, the fixture monitoring system takes care of it. And any change in or rapid drop in the pressure can trigger an automatic alert and control shutdown of the machine when it happens. We modified the wireless temperature sensors and which was designed specifically for this fixture monitoring system. And the IoT gateway was repurposed as a receiver with display. And also we provided cellular signals for the cloud storage. So when in operation, each transmitter sends the parameter value such as the battery status, the fixture number, and transmitter serial number to the receiver on the other end every second. And if there is a loss or change of fixture pressure or load, the receiver can trigger and automatically control shutdown of the machine happens through the machine's PLC control system. It provided an extra layer of machine safety monitoring. It also reduced the product loss through the movement of the workpiece, loose workpiece when that happens, and enhance the system's safety. And the product it also protected against any sort of operator error, right? For example, starting a cutting cycle without first applying the correct hydraulic pressure. So the Sensata's product prevented that from happening. The next case study is about locomotive vibration monitoring. There was a requirement to obtain vibration data from a large fleet or locomotive where access to the sensor was impossible. Dynamic locomotive vibration monitoring can record the operating conditions of the locomotive during operation hours rather than just waiting for the regulatory inspection times. It results in more effective use of downtime because the parts can be targeted for repair based on the prior knowledge of the operating conditions. The existing tools such as hard bearing and dragging equipment detectors have been in place for a considerable amount of time, but unlike vibration monitoring, these units detect components that have already failed. So vibration sensor can monitor specific components and provide pre-failure notifications, leading to a long-term cost savings. The rail industry can benefit a lot from this, and we have proved that in the practice through the vibration monitoring system, where we had reduction in failures, and we had an ability to better schedule the maintenance of critical operating equipments. We installed both wireless and wired vibration monitoring systems that allowed to collection data of full vibration waveforms from remote and dangerous locations where otherwise the data could not have been possible to collect, which allowed more data to be collected and reduced the time to travel to the site for data collection purposes. We designed a special 50 kilohertz data acquisition system with real-time wireless transfer, and then also intelligent signal buffering. Our sensors were able to transmit the data using cellular signal and provide more information about the locomotives. And that's how we save the customers to avoid additional downtime. So the next case study is about a grain silo temperature monitoring. Grain silo temperature monitoring is overly critical for farmers around the world. These iconic structures that dot the landscape of farming areas enable farmers to store the grain efficiently. Silos are simple structures that do not have many high-tech components. However, they still require careful installation, operation, and maintenance. Grains stored under suboptimal condition can lead to insect infestation and rotting products. It can be prevented by measuring the temperature of the grain using easily installed wireless sensors acting when the temperature rises. Any temperature variation in the grain is automatically detected for quick action, avoiding any grain loss. Temperature is a key factor for maintaining the grain quality in grain storage system. When the grains have suffered from any sort of deterioration, corrosion or pest and disease damages, the temperatures increase to control that. And if precise temperature information of the grain can be mastered, an air conditioning system can be also used to effectively control and once we have to achieve the high efficiency energy management as well. It was a straightforward application for our existing wireless temperature transmitter and wipe port gateway. For silo management, we installed wireless temperature sensors, which sends data regularly to the gateway. The gateway then forwards it to the sensor data cloud for logging, displaying, and email generation. We were able to monitor the grain silo using this strategy. So the next case study is about embankment monitoring system. Typically, a transition zone have embankments, which are railway or highway supporting transition zones. And without timely maintenance, the differential settlement may cause any sort of damage to the track components or even may cause loss in passenger comfort. Historically, the monitoring teams have attended these sites to take manual inclinometers readings to ascertain how and where the failure could occur. Sending engineers to this site to collect the embankment data, slope data, is very expensive and can be also dangerous. And often the data that has been collected always have gaps or errors. The ability to collect the data automatically solves these problems, saves money, and also we can collect more data. For one of our customers, we mounted highly accurate dual axis inclinometers in boreholes, which were like up to 50 meters deep. We took regular measurements, transmitted to remote servers for display and reports and alarm generation. The base station received data from our sensors and transmitted it to the cloud-based hosting services to view the monitoring data. The sensor transmits data wirelessly to the base station. Wire-free systems allows the installation with minimal disturbance. One monitoring system takes inclinometer. Our system takes the inclinometer readings on an hourly basis and displays it on the live dashboard in an industry standard graphic format. The slope movement that can be seen over trend charts, right? Over a weekly, monthly, or quarterly time scales, we can look at how much the slope is moving, and it removes the need of engineers to travel to these difficult to access sites, and then also saving money and reducing the health and safety issues for these as well. We provided more frequent and comprehensive data, allowing remedial work to be done more targeted and cost-effective way for this customer. This case study is about a solar farm and how we remotely monitored using thermocouples, which enabled any early detection of high resistant joints and prevented overheating and increased the lifetime of these assets. So solar farms are inherently, they rely on remote monitoring to asset conditions like panel outputs. Monitoring for potential high resistant joints often involves planned manual inspection performed a few times a year during the cooler months when the temperatures are not high. Hence, the problem of hot spots are less likely to show up. Solar farms are prone to fires caused by increased resistant joints because the high currents generated and exposure to these large temperatures and humidity variations that happen. Even if the thermal imaging is done regularly, it does not provide continuous, reliable, or predictable data, give you that predictable data. This data scarcity makes it harder to analyze and trend any sort of joint failures, which occur often mostly in the peak summer hours when you're not taking any sort of you're not taking measurements there. And then the high ambient temperatures in the summertime causes production loss because of the increased joint temperatures. One customer of ours turned to Sensata's high. So one of our customers turned to Sensata's high joint monitoring solution. The solution provided real-time access to the temperature data for the solar farms terminals. Sensata also designed a flexible strip with multiple sensors for the use on a standard width fused terminal to enable quick and easy installation. A wireless transmitter is used to transmit the data digitally, digital temperature into the IoT gateway. And once the system was installed, so far, 2 high resistant joints were identified, which could have led to fires in the substation, which saved them up to $250,000. And due to the use of Sensata's remote monitoring solution, the customer reduced the maintenance of both DC combiner boxes and substations. And they were also able to detect high potential resistance joints up to 6 months in advance before the temperatures reach that critical value. Our systems monitor the temperature at critical terminals and also detects high resistance and loose joints, preventing any sort of damage and potential fires that may happen in the future. So the last case study we will be looking at is at one of our customers that manufactures overhead cranes and hoists. The chain drive driven by the motors were constantly failing. Due to the lack of accessibility, it was impossible to perform any type of analysis on the drives while it was in operation. The customer looked at other wireless monitoring solutions, online condition monitoring systems, but this did not solve the problem because they were not providing you the detailed vibration data, such as the time waveform and fast Fourier transformation FFT plots. They were just providing an overall RMS number, which was not enough to determine the root cause of the problem. So the customer turned into our smart vibration sensor 6VW, which has 6 in one sensing modalities packaged into one sensor. And we were able to take a rich vibration data for low frequency vibration. And then also we had acoustic sensor, which was taking data in the high frequency ultrasonic range. And also we were monitoring the temperature, speed using our Sensata IQ dashboard. And after a short period of time, the machine learning algorithm was able to pick an anomaly in the acoustic data. We were able to diagnose the problem with the chain drive lubrication. And then also there was some overloading of the chain drives issues as well. So this information allowed the maintenance team to attend to the asset and carry out immediate short-term adjustments to the motors and gearboxes, and potentially stopping unplanned downtime. So our system provides a full access, gives you full access to the data, and has the ability to send that data externally to a third-party analyst if you do not have vibration experts. Our system also, but you don't have to be a vibration expert in order to use our system. Our system has an AI-backed platform that can detect anomalies and notify the user when that happens, and then also identify the root cause of the problem, and also provide you remaining useful life information, and then also suggested action and how to fix those sort of problems. So these were the cases, the case studies I wanted to share with you. And I would like to mention one more thing, is that today's systems require a lot of high upfront costs, custom software, and then they need experts to install the solution. And that can be only justified. They're so expensive that can be only justified to 10% of the critical assets. Using the smart sensors, cloud software, and AI machine learning algorithms, our solution can create a digital twin of your asset and then also provide predictive and prescriptive insight at a very low cost. So tying everything back together, why is the market adopting the machine health monitoring solutions using predictive maintenance technologies? So here are some stats for you. So the average number of downtime per year for a factory is about 144, and the average annual cost of unplanned downtime or standstills for a factory is about $2.3 million. 32% of the billion-dollar manufacturers estimate that they will lose over 100 million as baby boomers retire in the next 5 years. 74% of the firms predict a shortfall of qualified skilled trade workers, according to the AGC survey. 31 million positions will be vacant due to baby boomers retiring again in 2020. And there's no other occupation in higher demand than the HVAC technicians. And that's why the market is turning towards using predictive maintenance technologies. So how do you get started in predictive maintenance? I would say the better question would be, how do you choose an online machine health monitoring system? So the idea here is to start with a pilot strategy. The first step is to think about a pilot program and identify what candidates can be chosen for remote condition monitoring. To pick the right candidates for pilot development, there are some factors that you should consider. First is pick assets with a high risk of failure. Look at the history of the asset. Some of the assets have more tendency to fail than the others, so you make a list of those. Know the impact of downtime. Is it just loss in production? Think about the production. Is it just loss of the production and so the final goods, or are you talking also about the loss in work in progress parts? Also, increased stress on your other production line if one of the lines goes down. And then also some fines that you may have to pay if you do not deliver on time. So it would be all important to consider for this, calculating the impact of downtime. Then calculate the duration of the downtime, the lead time, how long is it going to take to get those replacement parts, and how much time it will take to replace those parts. So you should be considering those. So once you look at these factors, find the right candidates to start the pilot project. And after the pilot is successful, you can start thinking about scaling it to more assets and fully implementing the solution. So once you have started the pilot program, if you have selected the right candidates, what should you look in an online condition monitoring system? The first is it should be easy to install. It should not take more than 10 to 15 minutes to install one sensor. It should also have right sensing modalities. Think about what type of sensor would you need for complete information, to give you the complete information about the health of the asset? Is it just temperature sensor or just vibration sensor or both? You should be picking up the right sensing modalities for that. Then also the data should the data should be rich and have good data analysis tools and the accuracy. Is it just the RMS number, for example, for using a vibration sensor data? Is it just the RMS number that can give you the complete information, or would you need like full-time access to full-time waveform and FFT information as well? So picking that will be critical. Also looking at solutions that have AI and machine learning algorithms to catch an anomaly that even can be missed by expert users of vibration, for example. And then accuracy will be the utmost important thing to consider. It should be easy to justify ROI. It should not cost you an arm and a leg to implement a solution. Think about ROI. Think about ROI being in months or days rather than like looking at years to pay back for the solution. And the last thing is it should be a scalable solution. It does not require it should not require additional infrastructure to implement one sensor versus 1,000 sensors. Those are the critical things you should consider looking into a machine health monitoring system. So that was the end of my presentation. Thank you for patiently listening to me. I would like now hand it back to Gary.
All right, thank you very much, Abhishek. Now he gets to answer some questions from the audience. So if you have questions, please type your questions for our presenter in the Ask a Question box on your screen. We'll get to as many as time allows. Any questions that we don't get to today will be posted online along with the archived version of the webcast. Also, remember to download a certificate of completion and a copy of the presentation. Just use the Event Resources tab on the left-hand side of your screen. All right, Abhishek, you ready for some questions?
Yes, I am.
All right, let's start with, how is Sensata's solution different than that of other IoT and preventive maintenance solutions available today?
That's a great question, Gary. So companies have been thinking about industrial IoT for decades now, but the challenge has been that the technology has created roadblocks more than a solution, keeping many of them from implementing the ROI goal they needed to be deployed for a solution, for example. Whether there is a challenge there could be challenges in the network, or could be accessibility or hard to deploy platforms. So Sensata's platform has been built from the ground up to deliver solutions to all those challenges. We leverage our wide breadth of industry-leading sensors, strong gateways and transmitters, and then also we provide actionable insights that can generally be managed using plant staff. That's how it's different from other providers today.
Got it. Fantastic. So how does this system differ from a typical industrial wireless sensing network?
Yeah, so the design of the existing systems is designed around monitoring only a plant's most critical assets and not for the balance of plant's equipment. Initially, I mentioned in my slides, it's only applied to the 10% of the critical asset, but 90% of the assets are not covered, right? So we provide a solution which will be able to will help you provide assets, covering more assets across the plant, making them, which makes the labor challenged maintenance operations effective and efficient. And also having wireless solutions that work outside of the PLC control environments makes it easy to implement, and also is very cost effective. We have automated alerts, AI-driven analysis, which reduces the need for internal domain and experts in niche areas such as vibration, and allows companies to cover more assets with using the internal team.
All right, fantastic. So where does the data analysis physically happen? Is it in Sensata servers? Is it local, edge computing? How does that work?
It depends on what type of sensors we are using. Some sensors transmit the data using the Sensata, to transmit the data directly using a gateway to the Sensata IQ platform, where all the analysis is being done in the cloud. But there are other sensors which are more capable of doing some edge computing, for example, a vibration sensor, where we detect the anomalies at the edge, and so the sensor sends data 3 times per day but it also has the capability to do some edge computing where it's constantly listening to this to the vibrations, and if say something happens, it sees anything out of ordinary, it will take data. So there's more. So some of the sensors are capable of edge computing. Some of them are. Most of the analysis is being done in the cloud.
Got it. All right. What industrial and factory problems did this product solve?
Sure. Unplanned downtime is one of the biggest one. So unplanned downtime costs millions of dollars. There are other labor challenges that I mentioned in my presentation. Like I mentioned, like the baby boomers are going to retire, so there will be a lack of labor force. So unexpected downtime, the costs are ever increasing than before. So because of all that, like industry, so we have a sensor platform that is over the top of the, which can be implemented on top of the existing infrastructure. It does not require any change in control platform or PLC related processes. That makes the system very scalable, allowing companies to roll out different types of sensors in different locations at different times, and then also reducing the cost of downtime and promise you better uptime.
Got it. What do you think are the main mandatory features for a predictive maintenance or condition monitoring solution to be successful?
Yeah, so in my last slide, I mentioned it should be, if you have to only consider like a few factors, right? So it should be very easy to install. It should not take you experts to install this. And the data should be intuitive enough, right? So if you do not have vibration experts, for example, you do not have experts to look at the type of data, the data should be intuitive enough, and then also it should be reliable, right? The sensor itself should not fail. So those are the three important factors need to consider.
Got it. Let's talk a little security. So how do you handle data security with wireless data communication to a central data monitoring center?
Sure. So we can send the data, right? So we have different protocols, but one of the we send data through Wi-Fi, or we send data through cellular communication. So we can bypass the planned Wi-Fi, right? If IT is very stringent, so sometimes the security vulnerabilities are created when you connect to the planned Wi-Fi. So we can go through the cellular data, but if you are going through the planned Wi-Fi, so the communication between our sensor and the cloud is like one way. So the cloud pings the sensor. So there is no two-way communication happening. So nobody can basically log on to our sensor to create a sort of hub. And then also the data we transmit to the cloud is fully encrypted. So there won't be any sort of problem with that.
Got it. Similar question here. What protocols are used for sending data from sensors to the gateway?
Yeah, so our portfolio is ever expanding. So we have started with Wi-Fi communication mostly, and then we use between our sensor and the gateway, there's a 2.4 gigahertz data transmission. But we are expanding our portfolio, right? So we have product roadmaps laid out to work with any industrial standard protocols like Zigbee or LoRaWAN. So we are able to use anything, Bluetooth, depending on what type of data we are sending, how rich the data is. Sometimes the transmission rate is going to be slower using a Bluetooth versus a Wi-Fi, right? So based on that, we will be determining what's the best solution for picking and choosing the protocols. So, but we will be able to work with most of the industry protocols.
Got it. And for everybody out there, we're getting toward the end of the presentation here. If you have any questions again for Abhishek, please type those into the Ask a Question box on your screen, and we'll keep getting to as many as we can get to. So how do customers use the Sensata IQ platform?
So, to give you an example of using a vibration sensor, so we send all the data to the cloud. We have lots of different types of trend charts, like RMS number trend chart. We have kurtosis and all sort of statistical charting that we provide to those customers. Customer also has access to full vibration spectrum data and vibration analysis. So the time waveform data and the FFT data. So we also other than the information we are providing, our AI system is basically doing statistical analysis in the back and is also providing information on a web-based cloud software. You just log on to you just type that URL in your browser, log on to your account, and then just start seeing all that information on the web browser itself.
Got it. Another question that came through is, do you have any examples that you can share for monitoring valves?
We have flow meters, right? So we have flow meters that we can implement, but we also have vibration, right? So depending on what technology is going to be useful, we are a sensor manufacturer. We are able to provide. We have a plethora of smart sensors, so we can implement whether it's a flow meter or a vibration sensor. Everything can be implemented on monitoring the valves. I think most critical part for monitoring the valve is going to be the ultrasonic range, ultrasonic vibration sensor. We do have that available. So those are the key sensors we can use to monitor valves, depending on what failure modes we are looking at. And we can adapt if it's possible to determine the health of an asset using any sort of technology. Chances are that we may already have it and we can monitor it.
Excellent. Very good question here. Are the devices and gateways approved for Class 1 Division 2 areas?
Yes, we do have most of our sensors are Class 1 Div 2, and then also sometimes we have other zonal ratings as well for the UL. So you can all that information is available to public on our website. You can go down, look at the data sheets, but most of our sensors have Class 1 Div 2 ratings.
Fantastic. Getting again toward the end here, this we'll probably just take a couple of more. In RUL estimations for equipment faults, do you consider the secondary and tertiary failure modes through your ML algorithms? If so, how? And then the second part of that, can you elaborate on the vibe port system that allows the collection of full vibration waveforms from remote or dangerous locations where otherwise data could not be obtained?
Yeah, so let me just think about that question for a second. So the first part.
I can do the first question and the second question. We'll take these two at a time.
Okay. So all right, that'll work.
Yeah. Sure. In RUL estimations for equipment faults, do you consider the secondary and tertiary failure modes through your ML algorithms, and if so, how?
Okay. To answer that question, the quick and short answer is yes. We will be looking at the secondary and tertiary failure modes. So our algorithms are trained. So it takes about 20 days for our algorithms to learn the asset. We basically go through the complete operational. We take more data points throughout that 20-day learning period. And any sort of deviation that may happen from that we have collected the signature of the asset that you are monitoring. Any deviation from that operationally is going to be flagged as an anomaly. So we will be able to detect whether it's if it's a primary fault mode, for example, if it's a looseness, using again example of vibration. If it's a looseness, unbalance, misalignment, we have a built-in library for those. But the AI is also capable of looking at the data that comes through, and then also we do we analyze the data and then sort of throw a flag if we see an anomaly, and start taking more readings to understand what that is. And we do also have a feedback system in our software where, if say you do a maintenance work in your on the machine and the data changes, so we have the ability to get an input from the user on what type of maintenance was done, so we can put that in our in the information, and then AI can get trained on that. So we do have that option as well.
Got it. Let's take the second half of that question, which is, okay. Can you elaborate on vibe port system that allows the collection of full vibration waveforms from remote or dangerous locations where otherwise data cannot be obtained?
Yeah, so our vibe port system, basically, you may have an existing IEP sensors or ICP vibration accelerometers, could be analog, single axis. So we can take that data from using the vibe port as a gateway, and the vibe port is capable of sending that data to the cloud. So we take all that information, and so everything that all the analytics that we have available can be applied to those data collected from the vibe port, and we'll be able to flag any sort of anomaly or any sort of fault modes that we see using that time. That we collect the time waveform data, but we convert that into a fast Fourier transformation FFT. Look at the frequencies, and then try to find the signature that are typical for any sort of fault modes.
Got it. You presented a number of use cases earlier. Do you have a use case of MHM and hazardous conditions like underground mines?
I think I'm not aware of this yet, but I can maybe get back. I can answer this question offline, give you more information provided, but I will definitely answer this question.
Excellent. Okay. Let's go with, is the cloud resource single or multi-tenant in nature? So is usage based on, what usage is based on which financial model, i.e. number of assets, number of transactions, et cetera?
I think there's some multi-tenancy built into this. We have full control of our software, right? We have the design control of our software. I may not be able to answer this question correctly right now, but I can maybe give you more information, get back to my technical team and get that information for you about the multi-tenancy, but we do have that option available.
Fantastic. I think we're going to take our last question here, so you're almost off the hook.
Sure.
Last question will be, what skills should students learn from predictive maintenance or hiring by Sensata?
So what skills should students learn for predictive maintenance?
Yeah, for predictive maintenance hiring by Sensata.
Yeah, I would say, so I'm a vibration category 2 vibration technician, right? That's how I would say was critical for me to get into my role as a product manager when I joined Sensata. So predictive maintenance, I think, is going to be required in the future, right? So the industry is changing. A lot of people are adapting the predictive maintenance practices. So I think ideally it would be a lot of students are now looking at the algorithms, right? So AI, they're learning about machine learning. I think those are going to be critical in the future. As we collect more data, we generate more insights. All the data has to be analyzed, right? So analysis of the data and then also looking at the machine learning techniques. Those are going to be important things to look into future.
Excellent. Everyone, thank you so much for all the great questions. And thank you again to our great speaker, Abhishek Jadhav, for sharing his time and expertise. Thank you, Abhishek.
Thank you very much, Gary.
I would also like to extend a special thanks to our sponsor, Sensata Technologies, for sponsoring today's event. Now that we're just about done, we're not quite done, we still want to hear how we did. An exit survey will pop up on your screen as soon as this webcast ends. Please take a moment to complete it because we use this information to improve our future webcasts. Finally, on behalf of Plant Engineering and Sensata Technologies, I'd like to thank you for attending. This concludes our webcast. Thank you very much, everyone. You guys have a great day.